My name is Timothy Costigan. I work at Nitro, but today I'm not going to be talking about PDF rendering, but rather a personal project of mine that I've been working on over the last 4 months or so as my pandemic project, and that is a PlayStation 1 emulator. Although this talk is kind of going to be a bit of an intro into some concepts in emulation and how you might structure an emulator. It's not going to be particularly code dense or even text dense, and while I don't make any specific mentions of C++, the code examples will be in C++, and I think you'll find it is a natural fit for writing emulators because it has the high-level and low-level features that you're going to be using a lot in an emulator. So talk's going to be broken down into me basically talking about why you might want to write an emulator. Then I'm going to talk about just some of the kind of key concepts of emulation, and then I'm going to go through the kind of structure of a system, the system in this case being the PlayStation 1. Although I think you'll find it's very similar to a lot of computers, and especially computers from the 90s and I guess 80s as well. So why would you want to write an emulator? Well, in my case, it was partly nostalgia. I grew up with the PlayStation and played a lot of games on it with my dad. But also as a practice project, it's quite similar to making a game where it kind of exercises all of the programming muscles. You're doing a lot of low-level and high-level programming. You're doing graphics and assembly language and sound if you get that far into your emulator. But beyond a little toy program, there is a practical use to emulators. We can see with Apple's announcement of switching over to ARM, that they've got the Rosetta 2 emulator so that they can run their older Intel programs on their newer ARM processors. And also, there is a fair bit of legacy code still running in the world. I imagine a lot of it is emulated now, but if you imagine, let's say you have a company that's running an old PDP-11, probably unlikely, but for sake of argument, a computer that old, if anything broke on it, you'd have to scavenge museums for replacement parts. And if you needed to change the code, you'd have to scavenge retirement homes for programmers. And a full PDP-11 would take up the space of 3 blade server cabinets and take nearly a third the power of all those cabinets. If you wanted to still use that old code, you could write an emulator and run it on one process of one of those servers and save all the space and energy, and it just makes sense. So moving on from that, we're going to start talking about the concepts. So there's kind of two types of emulation that you can do. There's low level, or some people would say cycle accurate emulation, where you emulate every single part of the computer. So in all kinds of emulation, you're going to be emulating the CPU, most likely. Although in some cases, like the PS2 or the PSP, they used actually later revisions of the same CPU as the PS1, so they were actually able to get away with not emulating the CPU. But generally, you're always going to have to do that. But in low-level emulation, you're going to, for example, have to write the GPU yourself and implement all of the polygon filling algorithms and all the, the sprite rendering and all the interpolation systems yourself. And the reason why you might want to do that is because it's obviously going to produce results that are visually and, if it's the sound processing unit, auditorially the same as what you'd expect on the original hardware. But it's incredibly processor intensive to do this because you are writing code that's actually emulating all of the hardware and the chips. It's quite difficult to actually figure out those details. So often people will actually take scans of the circuits and they'll decap the silicon, usually with fairly noxious chemicals like fuming nitric acid. This is actually a GIF I took of a computer that's to the left of me that can do 3D scanning, but I never actually used this data. But I was planning to do this initially in my project. High-level emulation is much more common and a lot easier. You can cut a lot more corners doing this, and that's where you basically just emulate the CPU, but all of the other things like the graphics card and the sound units and everything are basically just very thin wrappers talking to modern libraries like OpenGL or OpenAL. This is something that allowed the Nintendo 64 and the PlayStation to be emulated in the early 90s, especially the Nintendo 64, which used a graphics chip designed by Silicon Graphics, who also had a big role in the design of OpenGL. So they actually had pretty much the same calls to the graphics card. So the relatively old MIPS processor could be emulated fairly easily back then, and the really expensive graphics side of things was already basically done by the modern graphics card in the computer. And this is the kind of emulation that I did in my project. So moving on. So when you're emulating the CPU, there are 3 different ways that you can go about it. There's interpretive emulation, which is the way you're probably going to start your project, and that's essentially where you have your binary program, which you load in and you parse it like a document, and you just break it down into its opcodes and parameters, and you run a function that matches what the original functionality of that instruction would be, and you just repeat. And obviously that means that for each assembly instruction you're going to have hundreds, maybe thousands of instructions coming out of your C++ compiler. But if you're emulating code that's written on a MIPS processor that was designed in 1988 on your i9, you can do this, and you don't even really have to think about performance. Another thing that has been tried but generally doesn't work is a thing called static recompilation. And this is where you get your binary program and you pre-process it into the assembly of your host processor. This generally doesn't work because things like branch offsets and potentially instructions talking to memory mapped peripherals won't match. There was one emulator that I can think of that did this, which was one for the original Xbox, and that only sort of worked because it was actually x86 to x86, and all the DirectX calls were the same because the original Xbox was basically the Windows 2000 kernel, fairly significantly stripped down. The other ways I meant to call dynamic recompilation, and for more modern systems, basically anything after 2000, or if you're emulating something like the PlayStation on a fairly weak bit of hardware like Raspberry Pi, you're going to have to do this. And this, at first, it is just interpretive emulation. And imagine you're jumping into a subroutine, because it's done on a subroutine by subroutine basis. Because it's a little bit more manageable if you do it this way. But when you jump into a subroutine in the machine code, you run the interpretive emulation as usual. You parse it, you execute it, and you repeat. But as you're doing that, you're also compiling out the assembly code that's the equivalent of this subroutine. And next time when this subroutine is called, instead of rerunning all that code, you instead run the code that you've compiled. Completely ignoring that. And this is how pretty much all emulation for anything like the PS3 or the Xbox 360 would do it. This is quite difficult though. There's usually lots of little bugs because you still have a lot of the same issues of offsets being wrong and memory mapped devices being wrong. And it also is quite difficult to generate machine code that will run. You could, I guess, embed a compiler and spit out DLLs that you hot load, or you could put the machine code directly onto the stack, but you have to change the attributes for the memory page to actually run code on it. But yeah, so moving on from that, now I'm going to go through kind of the structure of a device, in this case the PlayStation, and kind of talk about how you emulate the various parts. A lot of this is going to look quite similar to a computer architecture lecture, so hopefully it's not too boring. So the core part is obviously the CPU. I'm sure a lot of people here know this, but you generally have two different kinds of CPU. You have RISC, which is reduced instruction set computers, which the PlayStation's MIPS processor is, or you have CISC, complex instruction set computers, which Intel is. If you are doing low-level cycle accurate emulation, this would be quite significant because the complexity of the processor can be quite considerable, and the difference is quite considerable between them. So RISC computers typically have a very small pipeline and quite simple architecture, while the CISC processors, although more recently, have started going to much smaller pipelines. Around the Pentium 4 era, with net burst architecture, it got up to 31 steps in the pipeline, which they dropped because it generally just meant there were lots of pipeline stalls. And there's also more complex things like microcode and branch prediction and things like that. But if you're just doing high-level emulation, the more important thing is the size of the instruction set itself. So with RISC, you have a very small instruction set that just has kind of basic operations, and you have your very explicit load store architecture, so you only can access memory through those load and store operations. While with CISC, you will have considerably larger instruction set. It can be thousands of pages long, while the MIPS manual is only a few hundred pages for the instructions. The instructions can do a lot of things, so it's just more complex functions to emulate them, and they might be variable length as well, so it's a little bit more complex, the parsing of the document, because you might have to grab a lot more bytes than you would have expected. For the pipeline, this is the pipeline of the PlayStation, but it would be pretty similar to most processors, where you break down your instructions into these kind of atomic operations: the fetch, where you grab it from memory; decode, where you break it down in the control unit to the various parameters; execution, where you actually run those parameters; memory access, where you write or where you access memory for the instruction; write back, where you actually write the result back to memory. Imagine if it's the Pentium 4, 25, 26 more steps there, which I don't know the names of. If you are going to do this with low level, you will have to do this, and it will be quite complicated. But in general, especially with the PlayStation 1, you can ignore this and you can do everything sequentially. You can cut corners, quite a lot of corners in emulators. So how do you actually emulate a CPU? Well, you load your application, your binary, your ROM, which is signified here on the left, and you just create an array that represents your RAM. The PlayStation has 2 megabytes of RAM, so I just create a unsigned car array that's 2 megabytes in size, and you store the binary file in there, the BIOS in this case. It's little endian, but your processor could be big endian or little endian. The MIPS actually can let the user configure that. You just have a variable that's your program counter. This would just be unsigned integer, and that is just an index into your RAM. When it increments, it just points to another byte. You have an instruction register, which is just another unsigned integer, and that stores whatever 4-byte instruction is pointed to by the program counter. So this is basically doing your fetch, and then this is what you decode in the control unit. You're not actually implementing the control unit of the CPU, you're just doing some bit shifting and bitwise operations to break down the instruction. And once you've broken down that instruction, you do whatever the instructions say to the registers and the arithmetic logic unit, which is where you do the adding subtraction. And then you increment the program counter, you grab the next instruction. This is an example of what an instruction might look like for the MIPS processor. So this is a register instruction, and it's quite simple, and whatever computer you're emulating, you can find the instruction format in the manual, and usually you'll have an opcode which says what kind of operation, and then the later bits will be the indices for registers. So in this case, I believe this is an add instruction, so the 0000 at the start says it's a register instruction, and the function on the right-hand side, I believe, equates to add. So this adds the source and target registers and puts the result in the destination register. There are a number of other instruction formats. You have jump instructions where there's a 26-bit offset to go forwards or backwards in memory, or you have immediate instructions where this is how you hard code in values in your binary. So you can see it's only a 16-bit value that's possible. So if you wanted to put a 32-bit value into a register, you'd have to do two operations. To decode this, it's as simple as you just shift and apply mask and store the value. Or if you're okay with doing something that's strictly speaking undefined behavior in C++, although generally works, you can use type punning, and this is something I do in my emulator because I'm using Visual Studio, where this is something that the Windows APIs extensively does, so I know it will work. And this is where you have a struct which has bit fields, and when you put something in value, you can read those values straight out of the struct. It makes the code a lot more readable, but technically you're not supposed to do it, but I do that. So in a nutshell, this is kind of what a simplified emulated CPU would look like. You grab an instruction, you do your bitwise operations to get the parameters, and then you use the opcode as a case in a giant switch statement. Each case will just have the very simple function that instruction is supposed to carry out in it. You could use the opcode as a key in a map of function pointers if you wanted. You can do all sorts of things, and that's originally how I actually did it in my emulator. But really, you want to have it in this tight loop, which if you have it in a nice switch statement, it might actually put all of it in a single cache line, and you'll get much faster performance. If you use any of the STL containers in the main loop of an emulator, especially in debug mode, it actually will drastically lower your speed. So you kind of want to roll your own containers if you can. An example of how slow it is, when I was using I think it was a single vector in this loop, it took 15 minutes for the boot logo of the PlayStation to appear, and it took a few seconds when it was removed. So moving on, less common now, but it's certainly back in the 90s, CPUs often had coprocessors. The PS1 had the system control coprocessor, and these are accessed through specific coprocessor assembly instructions. Strictly speaking, it wasn't a coprocessor, it actually was on the chip. I presume it was a late design addition to the CPU. And this just held hardware registers that stored the state of the system, what endianness was being used, what memory space was being used, if it was in an exception, what caused it, and more importantly, it controlled interrupts. So there were hardware lines connected to all the various peripherals like the CD-ROM and the GPU and various timers that when set active would trigger an interrupt. And an interrupt, basically imagine you have a peripheral that's quite slow like the CD-ROM. When you send it a command, you don't want the CPU to be sitting around waiting. So it would instead send the command and then continue about its business, and it would wait for one of these interrupts. and when an interrupt would be fired, it would save the state of the CPU, so the program counter would be saved and various other state values. And then the program counter would be set to an exception vector address, which would contain code that would check the system control processor and also the various hardware registers to see what happened and to handle it. So if it was the CD-ROM, it would know to tell it to read or tell it to seek. And once it finished handling this exception, it calls a restore from exception instruction, and that restores the state that it saved, and the CPU continues about its day. So the other coprocessor is something called the geometry transformation engine. And actually, on most MIPS computers, this was where the floating point unit was. But on the PlayStation, they decided to omit a floating point unit, and they put this in. And this was the secret sauce of the PlayStation. It's basically a linear algebra library on a chip. I guess it's similar to like a single instruction, multiple data setup, and it has registers where they could store matrix values, and then you could send commands to it to tell it to do matrix multiplication and interpolation and things like that. And it's the reason why the PlayStation, with its at that stage 6 or 7 year old processor, was able to do hundreds of thousands of triangles at a time when PCs could only do a few hundred. Generally, you're not going to get any performance benefit emulating the exact operation of the geometry transformation engine. So in an emulator, you're really just going to be implementing the interface for it and then doing all the calculations with something like GLM on the background. So for anything that isn't on the CPU itself, and obviously the coprocessors, you have to talk to them through the memory map. So imagine you have this, or this is the address space for the PlayStation. So it's multiple gigabytes in size, but the PlayStation did not have gigabytes of memory. It only had 2 megabytes of RAM and 1 megabyte of VRAM. So how was this broken up? Well, it was broken up into various segments. On the N64, I believe, which uses a very similar processor, it had virtual addresses, and it would be a little bit more complicated to implement it there. But on the PlayStation, they just mirrored the first 3 user segments. So if you called 00000, it would be the same as if you called 80000. And at the top of this address space, the RAM would be mapped. So if you called anything between 0 and the first 2 megabytes, or the same in any of the other 2 memory spaces, just offset, you would get the RAM, and at the bottom they stored the BIOS, so the operating system of the PlayStation. And in these gray areas in between, they would map the various peripherals, the game pads, the GPU, the CD-ROM, the direct memory access, the parallel port. So when you called those addresses, you didn't get memory, you got a direct line to that piece of hardware. So to control them, you would call well-defined addresses for things like the instruction register of the CD-ROM or the data register of the CD-ROM. And if you read that, you would get what it had read off the disk. The bottom segment was not really used on the PlayStation. There's one area of it that was mapped to a cache control system. So I'm going to go through a few of the peripherals that might be connected, just to give you an idea of how they work. So the CD-ROM was one of the key selling points of the PlayStation. It actually, I think even now, is considered one of the best audio CD players in the world. They put a lot of effort into it. The original PlayStations are often advertised as audiophile PlayStations. And the CD-ROM in the PlayStation was between 1 and 2 times speed. So most of us would remember 52 times speed CD-ROMs, but this quite early CD drive could only read between 150 kilobytes and 300 kilobytes per second. So at 2 megabytes of RAM, it would take between 12 and 6 seconds to load. And that's assuming everything is already in a line ready to be read off. That's excluding seek time and things like that. So the CPU would talk to something like this, and a hard drive on a computer would be similar. So it would talk to it by setting an instruction hardware register that's mapped in the address space to have a seek request instruction. And then the CPU would continue about its day. CD-ROM, though, in parallel, would begin that seek. So on a CD, you have various sectors, and the laser might not be anywhere near them, so it has to move, which can take, I guess, a few milliseconds. So once it gets the request, it would send an acknowledgement back, which will cause an interrupt on the CPU, and then the CPU handler would either check the CD-ROM to see if it needed to do something, or would just continue about its day. Once the seek is complete, a similar thing would happen. The CD-ROM would trigger an interrupt saying, oh, I finished seeking, and then the CPU would call its handler and would tell it that I want to read the data that I've asked you to seek. It would then start reading off that data, and once it's finished, it would have acknowledged that command, and then it would confirm that it had read, and then it would spit back to the CPU the data. The data can either be read by accessing a memory mapped data register on the CD-ROM, or through a direct memory access operation, and that's generally how it was done, and I'm going to detail how they work in a moment. Because this is just more an interesting tidbit, because the CD-ROMs were so slow, especially in the early days of the PlayStation, it was quite common to have very little of the CD-ROM actually used, and instead they would just duplicate the same game multiple times throughout the disk, so that the seek time would never be that high. Another interesting thing is that Sony integrated into the mastering of the CDs their copy and region protection system. So when printing their CDs, they induced a deliberate wobble in the sectors, which all CD drives would correct for and read normally. But unlike normal CD drives, the PlayStation actually read in the variations in that wobble, and it turns out they are ASCII characters encoding the region of the disk. So if the BIOS, which has encoded what the region is, doesn't see the same region as it's expecting, it won't boot any further. So for America, it would be SCEA that would be returned back, so Sony Computer Entertainment America, SCEE for Europe, and SCEI for Japan. There was also a consumer dev kit called the Net Eurose that they released that would return zeros. They're highly sought after now because, well, obviously they're dev kits that you can purchase legally. Anyway, another GPU, or another peripheral, and probably the most interesting one on the CPU, sorry, on the PlayStation to implement is the GPU. The PlayStation had a 1 megabyte frame buffer, and this was also where you stored the screen you would actually output to the TV, but also the memory for the textures and color palettes was here as well. There was no separate texture units or anything like that. So the higher resolution the game, the less space you had for textures for that game. The internal frame buffer was something around 720p, but in practice, because of the limitations, you rarely see games that are higher than 320 by 240, and the highest resolution that was supported was 640 by 480, but I don't think any games use that at all. The color space was 15 bits, which means that for 1 pixel you needed 2 bytes. So it would be 5 bits per color channel, and the final 16th bit would be used for a transparency flag. It could do 24-bit color in special circumstances. It had a thing called the MDEC, the motion decoder, which was very similar to an MPEG-2 decoder, and it's what did all the FMV cutscenes on the PlayStation. And I believe it could do 24-bit, but in general, most games were 15-bit. Because of the limited texture space, you also could do color lookup palettes. So you would store pixels in a texture not as 16 bits really, but as either 4-bit indices or 8-bit indices, allowing either 256 colors or around 16,000 colors if it was 8-bit. And how these works is you would store in your frame buffer a one-dimensional texture, which would have all of the 15-bit colors that you intended to use in that texture. And when you would then use that texture in the frame buffer, you would use that index to select the correct color from that palette. It didn't mean that you only had 4-bit colors. It just meant that you could only have 256 15-bit colors. So a side effect of the lower color resolution on the PlayStation and a lot of consoles at that time is that you get artifacts like color banding. I've simulated it here, the top gradient. I'm not sure if it comes through on Zoom, but the top gradient is what you'd expect, but you're going to see a lot of PlayStation games this quite noticeable step between each gradient in the gradient. And on the early PlayStations, there was actually a hardware flaw in one of the interpolation methods that meant, I believe it was 3-bit interpolation, so banding is quite severe. An interesting thing that people would probably see a lot in games now when they're emulating them is this thing called dithering. So you'll see a lot of textures where between two colors there'll be dots kind of transitioning over. And a lot of people forget that at the time, high resolution displays were not common, and the PlayStation certainly wouldn't be connected to one. And on a cathode ray tube, it would not actually have the resolution to draw these dots, and instead it actually would come out like a relatively fine gradient. So in your emulator, you might actually want to apply some sort of scan line blurring to replicate that effect. An interesting thing about the GPU on the PlayStation is it lacked a Z buffer or depth buffer. And this is the reason why the PlayStation has a fairly iconic affine texture warping problem, where you see the kind of textures swim as the camera moves. And this is because imagine you have this kind of squat triangle here on the left. The PlayStation only has two-dimensional data on the location of its vertices. So it has no idea whether it was supposed to be a squat triangle that is parallel to the screen or if it is an equilateral triangle that's at a very severe angle. But it treats it functionally as if it is parallel to the screen. So when you're doing texture mapping, you visually expect it to kind of go towards the horizon so the texture to go towards the horizon and gets more distant towards the tip of the triangle, but instead it's textured as if it's dead on. Obviously, if the triangle isn't at a severe angle, you wouldn't notice this effect at all. So games are often designed around this to keep the camera from ever letting you see triangles at these angles, or they would have geometry at a very high resolution, which obviously would make the game run quite slow, but it would minimize the effect of this because you essentially would have more points between interpolating. And another side effect of having no Z buffer is the PlayStation doesn't know the order in which the triangles have to be rendered. So if you have a 3D camera and you're not changing manually the order of the rendering, you're going to see triangles that should be concealed by a triangle in front of them, been drawn the other way around, and things will look completely wrong. But they do something interesting with their direct memory access system to work around this problem, which I'll talk about now. So the DMA, or direct memory access, is a chip on the PlayStation, and most computers generally have something like this. And this allows the computer to do kind of batch memory transfers between a device and RAM, or RAM and a device. So the CPU would talk to this chip, again through memory mapped hardware registers, and it would send parameters saying the start point in memory of the device and start point memory of the RAM, how many bytes it wanted to copy, and which direction it wanted this copy to go. The CPU would then go dormant, so it's not executing instructions, but because everything's now being batched, it generally is a lot faster, because instead of the CPU having to read from RAM, put it into a register, then read from the register and copy it to the device, it's just going straight to the device. The PlayStation has another DMA mode called the linked list DMA mode, and this is how it handles that rendering issue, the order of triangles. So imagine in memory you have these rendering commands, and the instruction on the PlayStation to draw a green triangle, it's not one instruction, it's actually 4 or 5 4-byte instructions. So there's a command, and then there's the parameters for the vertex locations and the colors and things like that. So if you wanted to change the order of these rendering triangles, you would have to copy the instruction for rendering the green triangle down to be after the blue triangle, and you'd have to, basically you'd be copying a lot of bytes all around memory, and it would take up a lot of cycles. Instead, they use this thing called linked list DMAs, where they have sprinkled throughout memory the rendering instructions, and also a pointer to the next rendering instruction in memory. So all you had to do was rearrange the pointers, and when you executed the DMA command, it would send all of the rendering instructions in the correct order. So it's a lot quicker to rearrange these than to move all the instructions around. Okay, I'm now finished with the kind of general structure of the PlayStation, but a few quality of life features that I've added to my emulator, and what I recommend people add to theirs if they decide to implement one, are save states. There's a reason why pretty much every emulator has save states. It's not just to let you cheat in boss fights. It's a very big help when you're debugging. When something goes wrong, you can easily roll back to a previous state, especially when you're in the early days of writing an emulator where performance isn't great. You don't want to wait minutes for you to get back to where you were before. You can do this quite simply. You just have to do a mem copy of your RAM and the various hardware registers and write it out to a file, or you can use C++ streams. The C++ streams are great because you're able to obviously write those out to a file or also into memory, which I find useful for creating a replay feature. I recommend also creating your own little disassembler. So with pretty much the same code that you use to parse your code, you could also easily print out the opcodes and the parameters, and you print that out to a screen, and you've basically got a disassembler, and you can see in a much more human readable way what your emulator is doing. Adding a memory viewer is essential, just so you can see what is being written out to RAM or to those hardware addresses. Adding breakpoints, so you could have it break when peripherals are being accessed or when values are changing. And a really useful thing you should add is time travel. So if you have fast enough save states, you could constantly be saving the state of your emulator so that you can do backward steps. And that's what I do in my emulator. So we're near the end of the presentation now, but in conclusion, here's some animated GIFs of my emulator in operation. These are just kind of features of it. It has a console so that you can kind of add in new functionality, new debugging tools without cluttering up the interface. This is all done with Dear ImGUI, so that you've got graphs for interrupts, so you know what devices are trying to take control. All the registers are being drawn out. All the registers for the CPU, the coprocessor for DMA. We're nearly at the end of this GIF here. There's the memory viewer, and just after this, it will show you the disassembler. One moment. So I added to this actually the ability to write comments, so I could run through the BIOS and kind of interpret how it was working myself, and it would save these comments out to a file so I could see them later on when I'd be doing new debugging sessions. And the final demonstration here, this is running just a custom little program. It's not running the PlayStation BIOS here, but this just demonstrates it running some GPU commands to draw a red triangle. It's not particularly interesting, but just to show you that it does work. And that's it.
So just a question on the DMA side of things. I know from playing around with kind of the Amiga and a few other things, the DMA processor and the CPU would tend to compete for memory. I don't know if that's something that the PlayStation has a problem with.
Not in the PlayStation. In the PlayStation, when there's DMA operations happening, the CPU sits idle. It doesn't work.
You just cannot run CPU instructions while the DMA engine is running.
Yeah. So typically, very small bursts of DMA instructions are executed because otherwise it would sit there for quite a long time.
Okay.
I presume that is a design decision to get around that.
Right. Yeah.
Because otherwise they would be stepping on each other's toes.
Right. The Amiga used to do this thing where it would, the DMA engine would kind of come in and come out again, and then the CPU would step in. And well, actually, as you were reading the frame buffer, like you'd kind of be reading every off cycle for the graphics, and then the even cycles would be for the CPU. Yeah.
Cool.
Okay.
Oh, there's some questions here. In one of the instances in your talk, you mentioned that STL vector degraded the performance. Can you throw more light there? Yeah. So. Obviously, in release mode, a lot of the issues with the STL containers are alleviated. They're optimized. All the extra code it adds is optimized out. But in debug mode, there's a lot of extra code. There's a lot of memory checks and things like that that are added in. So you would expect, this vector to have only a few instructions, but it could be hundreds of instructions in debug mode. If you're asking about the specific vector problem I had, I think I just had, it's been a few months now since I had this problem, but I think I just had registers or something like that as a vector rather than just a normal array. And just when you were accessing it, sorry, is it specific? Yeah, so the Microsoft vector definitely makes it a bigger problem. It wouldn't be as bad if you weren't using Microsoft's implementation of vector. And it's not like they've implemented poorly. It's for your own safety that they've added all those things. And if you weren't writing an emulator, you generally benefit from all those extra checks. They'll catch a lot of mistakes you've made before you've let them get to commercial code. Any other questions?
Have you got the source for it on GitHub?
I do actually. I didn't add it in here, but it's all open here. I can type it in here if someone wants it, or after the chat, if anyone wants it, I'll give you the GitHub. But it's all open. If you look at the the GIF here, it says PSX Emu Mark II. That's the name of the repo as well. So you can find it there. But if you reach out to me, I'll send you the exact GitHub link.